Assalamu alaikum students. Today we are going to discuss very important topic of neural networks. Neural networks are also known as artificial neural networks or simulated neural networks are a subset of machine learning and are at the heart of deep learning algorithms. Their names and structure are inspired by the human brain mimicking the way that biological neurons signal to one another. We can use neural network for a number of applications. We can use neural application like in financial services from forecasting and marketing research to fraud detection and risk assessment. This is a basic structure of artificial neural network. Here we have set of nodes with inputs and outputs. These are the inputs. Inputs can vary, it depends on the problem. And here we have output. Inputs are multiplied by weights, and then we apply activation function on them to produce output. The connectivity between the nodes and the different layers provide a network architecture. Neural network computations depends on connections and weights. And with the help of neural networks, we can calibrate weights depending on the required output. And this is a most powerful feature of neural networks. In this lecture, we will discuss how we can build a neural network to solve a problem of XOR network. Here is the XOR function. In the XOR function, if we have same inputs, like if we have 0 and 0, then output will be 0. And if we have 1, 1, then output will be 0. In case of different inputs, we will get 1. In this example, we will take this scenario. We have inputs of 1 and 1, and our targeted value is 0. Now let's solve this problem. We have inputs 1 and 1, and our required output is 0. This is the architecture of the neural networks we are gonna use to solve this problem. In this network, we have a single hidden layer with only 3 neurons for this example. And we have selected random weights between 0 and 1 and assigned them to connections from each input to the hidden layer neurons. And from hidden layer to outputs. And here we have 0.8, 0.4, 0.3, 0.2, 0.9, and 0.5. We sum the product of the inputs with their corresponding set of weights to arrive at the first value for the hidden layer. You can think of the weights as measures of influence the input nodes have on the output. Like here we have input, which is 1, and weight is 0.8. We will multiply this input with weight 1, which is 0.8, and other input which is coming on this neuron is from this input, which is 1, and multiplied by 0.2. So we have 0.8 into 1 plus 0.2 into 1 coming at hidden layer on this neuron. And we get 1. In the same way, we can calculate 1.3 and 0.8 0.8 on these neurons of the hidden layer. After calculating these weight and input product, we can write them on the hidden layer. These are not the output of this input layer at hidden layer. We have to apply activation function. We are going to use sigmoid or logistic activation function because the sigmoid activation function curve look like a S shape, and it will provide us values between 0 and 1. The sigmoid function is used in the cases where we need an output which is ranges from 0 to 1. The main reason why we use sigmoid function is because it exists between 0 to 1. Therefore, it is especially used for models where we must predict the probability as an output. Since probability of anything exists only between the range of 0 and 1, sigmoid is the right choice in our example. Sigmoid function is differentiable. That means we can find the slope of the sigmoid curve at any 2 points. The function is monotonic, but function's derivative is not. The logistic sigmoid function can cause a neural network to get stuck at the training time. The softmax function is more generalized logistic activation function, which is used for multi-class classifications. Here we have discussed derivative. Why is derivative and differentiation is used in neural networks? When updating the curve, which is produced by activation function, to know in which direction and how much to change or update the curve depending upon the slope. That is why we use differentiation in almost every part of machine learning and deep learning. This is a slope which is produced by the sigmoid function. This function can easily be calculated from the scientific calculator, or you can use this link to get the values of sigmoid function. As we have seen, we have 1, 1.3, and 0.8 values on the hidden layers after multiplying weights with the input. Now we have to apply sigmoid function to get the output at hidden layers neurons. After applying sigmoid function, where x represent the value we have got from multiplying input with weights, and after applying sigmoid function, we have these values. Those are 0.731058 and 57863. And this is recommended to get the values up to 10 decimal point to get more accurate results. Now we have written the values, the results we have received after applying sigmoid function. Now we will proceed from hidden layer to output layer. In the same way as we have done from input to hidden layer, the weights will be multiplied with these results, and those are 0.73, 0.79, and 0.69. After multiplying, because here we have 3 arrows coming to output layer from these 3 neurons, so we have to multiply each result with corresponding weight to get the output. Once we have applied activation function, then we will get the values at output layer, and those are 0.774. But these values are not our target value because at input on SOAR function, we have to receive 0. So 0 is our target value, but our calculated value is 0.77. Because we have used random set of initial weights, the value of output neuron is off the mark, which is 0.77. In this case, by plus 0.77, since the target is 0, if we stopped here, this set of weights would be a great neural network for inaccurately representing the XOR operation. We need to calibrate these weights to get the required or target value. So here we have done forward propagation. This was the first iteration of the forward propagation. To calibrate the weights, we need to perform back propagation. Let's fix that by using back propagation to adjust the weights to improve the network. To improve our model, we first must quantify just how wrong our predictions are. Then we adjust the weights accordingly so that the margin of errors are decreased. Like forward propagation, as we have done earlier, back propagation calculations occur at each layer. We begin by changing the weights between the hidden layer and the output layer. We will start from output layer to input layer, and that is why this is called back propagation. Calculating the incremental change to these weights happen in two steps. We find the margin of error of the output results, what we get after applying the activation function to back out the necessary changes in the output sum. We call this delta output sum. We extract the change in weights by multiplying delta output sum by the hidden layer results. The output sum margin of error is the target output result minus the calculated output result. And here we can solve this. We have target 0, but our calculated values are 0.77. So we minus or subtract calculated values from target, and we can get the output sum margin, which is minus 0.77. So we need to adjust this error, and we need to calibrate our weights to produce 0 outputs. So to calculate the necessary changes in the output sum or delta output sum, we take the derivative of the activation function and apply it to the output sum. In our example, the activation function is sigmoid function. The activation function sigmoid takes a sum and returns a result. This is how we perform sigmoid function on the sum. We apply sigmoid function on the sum and we get the results. So the derivative of sigmoid, also known as sigmoid prime, will give us the rate of change or slope of the activation function at the output sum. So this is how we can calculate the output sum. We need to take the prime of sum, which is delta sum, d sum over d result, derivative of sum and derivative of result. Since the output sum margin of error is the difference in the results, we can simply multiply that with the rate of change to give us the delta output sum. And this is the formula to calculate S prime or sigmoid prime, which is S prime is equal to 1 over e raised to power x into 1 plus e raised to power minus x and whole square of 1 plus e raised to power minus x. This is how we can calculate the S prime. Conceptually, this means that the change in the output sum is the same as the sigmoid prime of the output result. So we can get the value in both ways. Doing the actual math, we get delta output sum is equal to S prime sum into output sum margin. Output sum margin we have already calculated, which is minus 0.77. Now we need to apply derivative of sigmoid function, which is S prime, and we apply this on sum. We have received 1.235, which is sum at output layer. So after applying this function, which is sigmoid prime, we will get the values, which is minus 0.134. We can also calculate this sigmoid prime from this URL. This is the curve we have received, and this is the values, this is the derivative of sum, and this is the derivative of result. This is the required sum, and here we can calculate the difference between the sum and the actual sum. Now we have the proposed changes in the output layer sum, which is minus 0.13. Let's use this in the derivative of the output sum function to determine the new change in weights. So how we can use the mathematical definition of the output sum is the product of the hidden layer result and the weights between the hidden and output layers. This is how we calculate output sum. Hidden results into weights before hidden layers, and multiplication of both values is called output sum. The derivative of the output sum is derivative of output sum divided by derivative of weights from hidden to output layer is equal to hidden results, which can also be represented as derivative of weights is equal to derivative of output sum divided by hidden results. This relationship suggests that a greater change in output sum yields a greater change in the weights. Input neurons with the biggest contribution, higher weights to output neuron, should experience more change in the connecting synapse. Let's do the math. We have hidden results at hidden layer on 3 neurons are 0.73, 0.78, and 0.68. Now we need to calculate delta weights, the change we need to calibrate these weights, and those weights are from hidden to output layers. And we can label them as W7, W8, and W9. To get the difference, we need to use this formula, which is delta output sum is divided by hidden layer results. And what was the delta output sum we have already calculated, that is minus 0.13 will be divided by each this hidden layer result, and we will get minus 0.18, minus 0.17, and minus 0.19. To get the new weights, we need to add these values in old weights. After addition, we will get 0.1162, 0.329, and 0.708. And these are the new values of weight 7, 8, and 9. To determine the change in the weights between the input and hidden layers, so we have these two type of weights. These are called W7, W8, and W9. And these are W1 to W6. We have calculated these 3 weights. Now we have to calculate these 6 weights to get better results at hidden layer. So to determine the change in the weights between the input and hidden layers, we perform the similar but notably different set of calculations. Note that in the following calculation, we use the initial weights instead of the recently adjusted weights from the first part of backward propagation. Remember that relationship between the hidden results and the weights between the hidden and output layers and the output sum is we have hidden results into weights and we have calculated the output sum. Instead of driving for output sum, let's drive for hidden results as a function of output sum to ultimately find out delta hidden sum. So here we have delta hidden results divided by delta output sum is equal to 1 over weights of hidden to output layers. So also remember that the change in hidden result can also be defined as delta hidden sum is divided by delta hidden results. Let's multiply both sides by sigmoid prime of the hidden sum. So we get the values and those are derivative of hidden sum is equal to d of sum weight divided by weight hidden to output multiplied sigmoid of hidden sum. So we apply this formula here. Our delta output sum is divided by, this is what we have got. This is the delta output sum minus 0.134. And now it will be divided by the weights we want to calibrate. And those are W1 to W6. And we will multiply these values with sigmoid prime. And delta hidden sum will be minus 0.88, minus 0.0452. Once we get the delta hidden sum, we calculate the change in weights between the input and hidden layer by dividing it with the input data. That is 1, 1 in this case. The input data here is equivalent to the hidden results in the earlier back propagation process to determine the change in the hidden layer to output weights. Here is the derivation of the relationship similar to the one before. Now let's do the math. Here we have input 1 is 1, input 2 is 1. Delta weights is equal to delta hidden sum divided by input data, which is 1, 1. And these values we have already calculated. After dividing with 1, 1, we will get the same results. Now we need to add these values to old weights to get the new weights. So after doing this iteration, we have calculated new weights for W1, W2, W3, W4, W5 and W6. And now we have these new weights. Now we have applied these new calibrated weights, and after that we have applied one iteration of forward propagation. After forward propagation, the result is 0.69, which is better than 0.74. So in this way, after one iteration, we have already improved our network. In the same way, after doing number of iteration, we can come at our target value, which is 0. And this is how neural networks works, and we can calibrate weights to get our required values.